As we wrap up Unit 8, I have both good news and bad news for you. The good news is this is the last video of Unit 8, so, well, I guess that's good news, right? The bad news is we're about to do some real gas stoichiometry with the ideal gas law. So this, again, is kind of the pinnacle of this particular unit, and put on your seatbelts because it's about to get real. Um, anyway, so what this basically is in the previous videos, I showed you what gas stoichiometries looks like if we're going from one gas to another gas. If we're going from one gas to another gas, then it's very simple. You just use the mole ratio because, again, they're related to each other through the chemical equation. Now, what we're about to do is some gas stoichiometry, but we're going to go from maybe a gas into something else where it's not two gases. And so this is going to require at some point an ideal gas law in order to find the moles to go into volume, or from volume into moles, perhaps into grams. So again, it's going to require a little bit of stoichiometry, like the previous videos that you guys just watched, and also the ideal gas law. All right, so number one, again, I'm going to go ahead and balance this equation. We have two chlorines on the left, so I need two chlorines on the right, which means I need two silvers. I'm going to go ahead and put a 1 there so that I know I'm finished balancing and I don't neglect that. The question says, what volume of chlorine gas, so notice we're looking for chlorine, okay? That's compound A, if you want to call it, or compound B, I suppose, measured at 17 degrees Celsius and 0.950 atmospheres, will be required to react with 0.5 moles of silver. So again, we're going from silver into chlorine. So we're changing compounds from one to another, and we're also going from moles, 0.50 moles of silver, into volume of chlorine gas. So again, that makes it a little bit more interesting. So what we're going to start with is our moles. Again, we're not going to start with our temperature. We're not going to start with our pressure because I don't really know what to do with that, right? And I can't go directly into the ideal gas law because our moles is in silver, yet everything else is for chlorine gas. So I can't go directly into the ideal gas law. I am first going to need to convert 0.50 moles silver Kg. And I'm going to convert into, or excuse me, out of moles of silver and into moles of chlorine gas, which is what they want. So again, this is going to be an easy part because we know from the previous videos, I just need to use the mole ratio as I said a few minutes ago. So there's my silver, that's going to be a 2. There's my chlorine, again, that's a 1. Therefore, when I do the math, I'm trying to change my color, it will not let me choose my color. There we go. Then I'm just going to divide by 2, so that's going to be 0.25 moles of chlorine gas. All right, now that I have my moles of chlorine gas, what I need to do now is now plug that into the other numbers that are all associated, with chlorine gas, which is going to be for the ideal gas law part of this particular problem. So now that I have that, I'm going to go to the ideal gas law. I'm going to have a pressure of 0.95 atmospheres. Again, there's my P. I'm going to look for volume because, again, I don't know my volume. I'm going to put my moles right here, which I literally just calculated. That's right there. Then I'm going to need an R value. My R value, notice my pressure is in atmospheres. So I'm going to use the appropriate, which is 0.0821 atmospheres liters per mole. And then I'm going to put in my temperature. My temperature is 17 degrees Celsius. So if I add 273, that comes out to be 290 Kelvin. So what I'm going to do now is I'm going to divide both sides by what is next to my V. So I'm going to take my calculator and go 0.25 times 0.0821 times 290 divided by 0.95. And what I get, let me try it again, getting something different, 0.25 times 0.0821 times 290 divided by 0.95. There we go. That looks more right, correct. 6.27. I think I miscalculated something on the previous attempt. And again, my unit of volume, it's nowhere in the question, but remember our unit of volume is in my R. It's going to be liters. Again, I have my number, my unit. I need to put my compound because we started with silver, but we ended with chlorine. So I need to distinguish that by putting liters of chlorine. All right, let's take a step back. In this problem, we were given chlorine gas was measured at a temperature and a pressure. So the temperature and the pressure both went to chlorine. Then they told us that is reacted with a number of moles of silver. Because that's the only number, for number for silver, that was our starting point. So we had to go from moles of silver into moles of chlorine. Once we had that, we had everything we needed for the ideal gas law to find the volume of our chlorine gas. So in this particular case, a one-step stoichiometric conversion before we did the ideal gas law. All right, now let's move on to number two. Number two, what we have here is we need to come up with a balanced chemical equation. So yay. How many liters of carbon dioxide gas at this can be produced from the combustion of octane? So octane is C8H18. This is a gasoline. If it's a combustion, I know it needs oxygen. And they already told us that it makes carbon dioxide, but I also know that combustion reactions produce water as well, ironically. So to balance this, if I am going to do my carbons first, hydrogen second, oxygens last, my carbons, I have 8 on the left, so I need 8 on the right. Hydrogens next, I have 18 hydrogen on the left, 18 on the right, I would need to put a 9. Now I'm going to go ahead and stop there because that's going to give me an odd number of oxygens. If you look right here, I have 16 oxygens plus 9. 16 plus 9 gives me 25. I cannot get this to be 25. That is not going to work. So that is not going to work, like I just said. So what I need to do is I need to double the 9, the 8 and the 9. So the 8 becomes a 16. This becomes an 18. And the 1 becomes a 2. All right, let me just double check, just make sure you guys follow my logic. So now I have 16 carbons. I have 16 carbons. I have 2 times 18, that is 36 hydrogens. Over here, I have 18 times 2, which is 36 hydrogens, okay? All that checks out. So everything, if I doubled everything, not surprisingly, it still works. But let's just check out our oxygens. So right here, I have 16 times 2, that is 32 oxygens, plus I have 18. Now 18 is a whole number, and I like whole numbers because on the left side I have a whole number of oxygens. So that gives me 50 oxygens. So I would need a 25 right there to give me 50 oxygens on the left, okay? That again is just a quick review of how to balance complicated combustion reactions. So in this particular example, it says how many liters of carbon dioxide gas, so we're looking for liters of carbon dioxide, at 27 degrees Celsius and a pressure of 560 millimeters of mercury can be produced from the combustion of 65 grams of octane. Notice the only thing dealing with octane, our starting point, is our mass. So we're going to have to start with 65.0 grams of octane, C8H18, excuse me. I'm going to go ahead and put grams down here to cancel out my grams of octane. And I'm going to put moles because, again, grams to moles is a very easy conversion. All right, that doesn't get me quite where I need to go because, again, I need to get all the way into something I can plug into my ideal gas law. In my ideal gas law, I have temperature, I am needing volume, I have pressure. So that means what I'm really missing is my moles. So if I put moles of C8H18 here, then I can convert into moles of carbon dioxide there. That will equal my N, and then I'll have everything I need in order to do the ideal gas law for the carbon dioxide. So on the first conversion factor, this is going to be 1 mole because 1 mole is equal to the molar mass of octane. So if I add up the mass of 8 carbons and 18 hydrogens, I'm going to cheat, and it comes out to be 114.232. Or let me just pretend I did that in my head, even though I clearly didn't. Then on the right conversion, when we have moles over moles, that comes from the table, or the equation, excuse me, C8H18, again, that's going to be 2. And then the top one, carbon dioxide is right here. That's going to be 16. All right, now I just need to calculate that out. This cancels, that cancels, and we'll be left with moles of carbon dioxide. So 65 times 1 times 16 divided by 114.232 divided by 2 as well gives me 4.55 moles of carbon dioxide. Now that I have that, I have everything I need for carbon dioxide. I have my temperature, my pressure, my volume, all for carbon dioxide, or excuse me, my moles. All I need now is my volume. So again, I don't know my volume, but I do know, again, this is my N, I do know my pressure, 560 millimeters of mercury. And I'm going to put my N, which I literally just solved, 4.55 moles. I'm going to put my R, again, the R that is associated with the millimeters of mercury. This is the one I often cannot remember. 62.4 millimeters of mercury liter per mole. Then my temperature into Kelvin. So 27 plus 273 comes out to be exactly 300 Kelvin. So I'm going to go ahead and take everything on the right, multiply it all together, and divide by what is next to my V. So 4.55 times 62.4 times 300 divided by 560 equals 152.10. Again, the volume, because of our value, my volume being liters. Again, because this is stoichiometry, I also need to indicate what volume of gas I'm talking about, and that would be of carbon dioxide. Remember, these the answers have to have a number, a unit, and a compound, so I know what the heck you're talking about. All right, so in this one again, what we needed was to go from grams into moles and then convert from moles of octane into moles of carbon dioxide. That way we have everything we need to do the ideal gas law for carbon dioxide. Once we did that, we easily plugged it in and got our volume. So let's move on to number 3. Number 3, what we have here is an equation which I'm going to go ahead and balance. My potassium and my chlorides are both balanced, but my oxygens are not. So I know that to get them both to be 6, I need to do this. And then to balance my potassium chlorines, I have that. So now it's balanced. So what mass of potassium chlorate, that's this, would be needed to produce 11.2 liters of oxygen at a certain pressure and a temperature? So notice the volume, the pressure, and the temperature are all associated with oxygen. So we need to then find the mass of potassium chlorate. So I don't know anything about potassium chlorate. So to me, this sounds like we're going to do this the complete opposite of number 1 and 2. We're going to need to do the ideal gas law first, because we have everything for oxygen. Once we get our N, number of moles of oxygen, then we'll be able to convert that into the mass of potassium chlorate. So like I said, this is a little bit reversed of numbers 1 and 2. So for my ideal gas law, I'm going to put my volume, 11.2 liters, times my pressure, which is 50.0 kilopascals, equals my moles, which I do not know, multiply by my R, ideal gas constant in kilopascals, which is 8.31, and kilopascals liters per mole. I'm going to put my temperature into Kelvin, which is 310 Kelvin. Again, that's my N. Sorry, it looks kind of like a funky letter. So what I'm going to do is I'm going to take the left side and divide it by the right side, because the right side has my variable. So 11.2 times 50.0 divided by 8.31 divided by 310 equals I got 0.22 moles. Again, this is for oxygen. Okay. Now that we have that, I'm going to take my 0.22 moles of oxygen. I'm going to put moles of oxygen down here, and then moles of what I want to go into, which is potassium chlorate, KClO3. Then I'm going to take, because again, they want mass. They don't want moles, they want mass. So I'm going to cancel out moles of potassium chlorate right here. And finally, I'll be able to finish at this step because that is my mass. So for the first step, we have our molar conversion. On the bottom, oxygen is going to be 3. On the top, potassium chlorate, that's going to be 2. Then on the right side, we have a 1 mole of potassium chlorate equals the molar mass. Again, I'm going to cheat. That's 122.55. All right, going to pick up my calculator, 0.22 times 2 times 122.55 divided by 3 divided by 1. And I get my final answer of 17.97 grams of potassium chlorate. Cancels, of course, that cancels. All right, so just again to talk through it one more time, this one is a little bit different than 1 and 2, only because they gave us everything we needed for oxygen, and everything we needed was for the ideal gas law. They gave us the pressure, they gave us the volume, they gave us the temperature. So once we were able to use that, we were able to find our N, or number of moles. Once we had the moles of oxygen, we had to do a little bit of stoichiometry to get it into not the moles of potassium chlorate, but the mass of potassium chlorate. So that required 2 steps. All right, last one. Let's go ahead and tackle number 4. Number 4, what we have here is, well, let me start off with the balanced equation. We have sodium plus water yields sodium hydroxide and hydrogen gas. So my sodiums are already balanced. My hydrogens look balanced, but they're not. As a reminder, what you guys may want to do, like I told you guys a long time ago, is convert this into HOH. Because I notice I have 2 H's there, that tells me I'll need 2 waters. That means I also have 2 hydroxides and 2 sodiums. That again is just a shortcut, which makes balancing these types of problems a lot easier. All right, now that I have that balanced, what we're going to do here is it says when sodium reacts with excess water, again, it doesn't matter if there's excess water, that's really not helpful. Wow. I just pushed a button and it did that. That was interesting. Let's try it again. With excess water, how many grams of sodium are required to produce? We have a volume, we have a temperature, and a pressure, all for hydrogen gas. So we're looking for grams of sodium, but we are given all these numbers for hydrogen gas. So kind of like number 3, the only thing we can really do is start with the ideal gas law. So I'm going to start with my volume, which is 6.50 liters. My pressure, now, again, it's collected over water, right? Over water at 30 degrees. That's really important. So I need to check my Dalton's law of water vapor pressure, look at the table, see at 30 degrees, what is the water vapor pressure? Now, they were nice in this particular example, and they gave us in parentheses that the water vapor pressure is actually 31.8. So what I'm going to do is I'm going to take my pressure, my total pressure, and I'm going to subtract out my water vapor pressure. So what that gets me is 640 millimeters of mercury. That is going to be my actual pressure of just the hydrogen gas. Again, I don't want to include the water and the hydrogen gas, but just the hydrogen gas. So that's where that comes from. Again, I don't know my moles. Nowhere does it tell me that. My R in millimeters of mercury, again, is going to be the 62.4 millimeters of mercury, liters per mole. And then my temperature, which was 30 degrees Celsius into Kelvin, which is 303 Kelvin. So I'm going to go ahead and solve for N, meaning the left side divided by the right side. In this particular case, 6.5 times 640 divided by 62.4 divided by 303, and I get 0.22 moles of what? Of hydrogen. All right, now what I need to do is take my 0.22 moles of hydrogen and convert it into what they want, which is grams of sodium. So to get to grams of sodium, I'm going to need to get into sodium first. So this is the step to do that. Once I'm into moles of sodium, I need to get out of moles of sodium and into grams of sodium. All right. So again, when we have moles on top of moles, just like always, that comes from the balanced chemical equation. On the bottom, we have H2. Here is my H2. It's going to be 1. On the top, oops. On the top is sodium. Sodium is right there, so that's going to be a 2. All right, on the right side, we have for every 1 mole, we have sodium, the mass of sodium from the periodic table, which is 22.98. I'm going to go ahead and get my calculator, put 0.22 times 2 times 22.98. Oops, I just said clear. Wrong button. 0.22 times 2 times 22.98 divided by 1, which of course will give me the same answer, which is 10.11 grams of sodium. There's my number, unit, and volume or compound. So kind of like number 3, we had to start with the ideal gas constant because again, we were given all these different numbers for our starting compound. Then in this case, they wanted to know the mass of a different compound. So that required the ideal gas law first, and then a little bit of gas stoichiometry second. All right, guys, I hope that was a very good review of how to do both the ideal gas law and gas stoichiometry all together. Again, you have to do this if we're going from, say, a gas to a liquid, a gas to a solid, or any combination of that, okay? Remember in the previous video, if it's a gas to a gas, all of this is not necessary, and all you would need to do is just use the balanced chemical equation mole ratios. Much more simple. All right, guys, thanks again for watching. Let me know if you have any questions.